Hi, in this video we are going to demonstrate the analysis of various non-linear high diameter models and fitting of various artificial intelligence based machine learning algorithms for high diameter relationships. Since height and diameter are very important dendrometric variables in forestry because they form the basis of the vertical structure of the forest. So in order to capture the relationship that exists between the height and diameter, we have a lot of non-linear high diameter variables available in literature like Nastland, Kurtz, Wyckoff, Power. These are the models which are usually used for accurate estimation or prediction of tree height utilizing diameter at breast height. But the problem with these kind of models while fitting in our console is that we have to fit each and every model individually utilizing a particular library, and we have to give the starting value to the coefficients which are very much required for capturing the underlying pattern between height and diameter. And apart from that, we have to apply the appropriate cross-validation techniques and so that we can be able to choose a model which is performing better utilizing some selection criteria like AIC, BIC or prediction error rate. So it is a hectic procedure, and another important thing is that there are some circumstances where these models predictions, they may be overestimated or sometimes underestimations will be there. So in order to overcome, we might use the conventional AI based machine learning algorithms for capturing the high diameter relationships. We might use decision tree, random forest, support vector or a gradient boosting. Again, we have to apply them separately. We have to write a code for this, we have to write an equation, then we have to apply the proper cross-validation technique. Again, it's a hectic procedure. So in order to overcome, we have two important libraries which are available in CRAN. One is ImFoR and ImHD. One is for nonlinear high diameter models, and another one is for these artificial intelligence based machine learning algorithms. So for that, I'll be using a data set which is already available or imported on my R console. This data set is based on 300 pine trees utilizing two variables. One is height and diameter. Here height is response or a study variable and diameter is considered as an explanatory variable. So I'll be using first IM library, and I'll be using the first library ImFoR for fitting of these non-linear high diameter models. Then I will write the name, the function, and I will write the default code ImFoR, then followed by the name of my data set and followed by this default function 0.8. Since train underscore frac is 0.8, it means that 80% of the data is reserved as training and remaining 20 for testing. If I will write 0.5, that means I'm using a half splitting method, 50% for training and 50% for testing. Then I will click on this enter button. Then I will write this model, the name which I have given to this whole function. Then press on this enter button, and you can see instead of writing all these codes, we have got the output results for each and every model, and we have the results for these selection criteria for coefficient of determination, root mean square error, mean absolute error, Kai's information criteria, prediction error rate across both training and testing, and all these results or output is also displayed in a graphical pattern. We have different graphs for these also, and based on these criteria we can choose which model is able to capture the relationship between height and diameter more accurately utilizing all these parameters or these selection criteria. So instead of using all these codes, within one click you have the results for all these non-linear high diameter models. Now in order to fit these artificial intelligence based machine learning algorithms, I'll be using another library, that is ImHD. Okay, for that I will be using the same steps which I have used for fitting of previous non-linear high diameter models. Here I will use a default code ImHD. Again, same steps, like first we have to write the name of our data. Here for training and testing we will use a different function, that is split ratio. I will write here 0.7, or I can write 0.8, 0.5 for partitioning my data. So because this is very much required to test the reliability of each and every fitted algorithm, and then I will press on this enter. All the results within fraction of seconds are available, and here gradient boosting can perform better in comparison to rest of the fitted algorithms. If I will write this model here, because this is the name which I have given to the whole function, then I will press on this enter. Here we are having the gradient boosting is having low values of prediction error rates, and you can find it out that these are the predicted values of based on this algorithm, decision tree, random forest, support vector machine, and gradient boosting. And as far as the prediction error rates are concerned, they are very low in gradient boosting in comparison to rest of the fitted algorithms, because a model or an algorithm is considered to be better or is considered to be best if it has low prediction error values, because these errors are nothing. It's the differences between the observed and the predicted values. The less the differences are, the more accurately that model is able to capture the relationship that exists between the variables. So these two libraries are very much recommended if someone is interested to do this, if someone is interested in these kinds of works. Hope these two libraries will be very beneficial, and hope you like this video. Thank you very much.